All right, so welcome back everybody for today's session of the Cardiff Analysis Seminar. Today we're delighted to have Matthias Schymura from BTU Cottbus-Senftenberg, who will talk about computing the covering radius of a polytope with an application to lonely runners. So thank you very much for accepting the invitation, and over to you.
Thank you very much for having me and inviting me to speak here. I'm happy to be in Cardiff again, be it online, be it offline. I will report on a joint work with three of my co-authors. Here you see them. This is Jana Slavicek from EPFL in Lausanne in Zurich. Then it's Romanos Diogenes Malikiosis from Thessaloniki in Greece. And then it's Marton Nasodi from Budapest University. The title was about computing the covering radius of a polytope with an application to lonely runners. And I want to present this title like from the back to the front. So I'm talking first about the lonely runner problem to get this talk started. But before I actually start, we already talked about this. So if you have questions, then just mute yourself and let me know and ask and stop me. Feel free to do that. So what's the lonely runner conjecture? The one, maybe one of you, one or the other has seen it already. I'm presenting it first in a setting that is due to Godin back in 1994. And the setting is as follows. You have n runners, and they run on a circular track of length 1 with constant velocities, and these velocities are pairwise distinct. And they all start at a common time and common place. So let's say here in the figure, you have the circular track of length 1, and they all started here in the north of this track where the flag sits. And at time t equals 1, say these 4 runners are in the respective positions that are shown here. And then we call a runner lonely at a certain time t if he's separated by at least a fraction 1 over n from all the other runners on the track. So n is the number of runners, and if they keep running, then it might be the case that there's a time for a certain runner where he or she is lonely. Meaning here, for example, at this time, the blue runner has distance 1/4 if he looks forward, and 1/4 at least if he looks backward to the next runner. So in this way, we say this runner is lonely at this certain time. And now the conjecture is, for each runner, there is a time at which she is lonely. So that's what the lonely runner conjecture is all about. They keep running, and for each runner, if you single out a single runner, then there will be a point in time at which she is lonely. And this gap of loneliness, this is 1 over n, where n is the number of runners. And this allows quite a lot of interpretations, and one interpretation that is suitable for geometric approaches, which I also want to present today, is the following, and this is what I asked you to keep in mind going forward. Like the distance of these runners, they only depend on the relative velocity. So what you can do then is you can look at the distance to the common starting point only, and say, well, the equivalent conjecture says that there is a time at which every runner is at least a distance 1 over n plus 1 from this common starting point. Right? So you make one runner run with 0 speed, so to say. So this is, as I said, more suited for geometric purposes. So this is what I will think about in the next slides and on all of the talk. So is the problem clear?
I have one question about this.
Yes.
This equivalent conjecture. So should it be switched a little bit? Because should it be for each runner there is a time such that the distance, because it shouldn't happen at the same, should it all be at the same time? So every runner?
No, it's not all for the same time. So each runner has its own time, so to say, when this happens.
Right. So it isn't
not simultaneously.
So it isn't a time such that every runner is a distance 1 over n plus 1, but for every runner there's a time.
Yeah, so what you basically do, so you have these runners with these n velocities, and since these distances only depend on like the relative velocities, you can subtract, say, the first velocity of every runner, and then you have a stagnant runner, and for this runner you look at when is this lonely.
That's clear.
This means distance from the starting point, and then this is symmetric with respect to which runner you actually made to have zero speed.
That's fine. I was just a little confused by the formulation of the equivalent conjecture, because it is like there is a time such that for every runner, this would like mean that you find a fixed time such that for all runners there is this condition.
Yeah, this is as I wanted to write it. So it's really, there is a time and every runner is away from the starting point. So this is like the time stamp for the stagnant runner, which then says that this stagnant runner, the starting point, is away by at least 1 over n plus 1 from everybody else.
Okay.
But thanks for the question.
Thanks.
Okay, so so this is like this picturesque formulation due to Godin, but this conjecture is much older, and this is due to Wills, and he was interested actually in Diophantine approximation. So I want to write down these things exactly and where this comes from. Yeah, and this is like a turnaround of Dirichlet's approximation theorem. And here I wrote down in one line what Dirichlet's approximation theorem actually says. So given a real number t and a natural number n, then you can find one of these numbers, 1, 2 up to n, such that if you multiply t with this number, then what you get is a number that is quite close to an integer. And this is measured by this distance to the nearest integer. And it says that one of these n numbers is a suitable multiplier for t 1 over n plus 1 away from an integer. Right? So this is Dirichlet's approximation theorem. And now the question is, can you find another set of numbers and get a better bound here? So like choosing q between 1 and n might be superficial, might be a very restricted scenario. So the question is it possible to choose another set of n real numbers here to take the multiplier q from and improve the upper bound that you can always guarantee? That's like the question, and Wills said the conjecture, no, you cannot do that. And this is exactly the Lonely Runner Conjecture that I presented you on the previous slide, because if you write it out, then it means that if you're given any n real numbers, this is those that you might want to replace the set of the first n natural numbers with, then there is a time t, or this real number t, such that all these numbers t times vi, they are far away from any integer. And the bound here is exactly this 1 over n plus 1. And you should think, and my notation suggests this already, about the vi as the velocities of these n runners that were running on the track. Okay. So yes, I said this is the conjecture that goes back to Wills in the 60s already, so it's quite old in the meantime, but there has been a lot of interest recently, but also over the years in the last 50 years. So if you have only one runner that runs on a track, then you see it's clear at some point it will be like opposite to the starting point, and this is what you ask for. Also for 2 runners, it's still quite easy. You can do this as an exercise to get more familiar with the problem maybe, but starting from 3 runners, it gets more and more complicated. And so people studied this and solved these cases for up to 6 runners. And for example, here for 6 runners, they make use of the fact that 6 plus 1 is 7 is a prime number. So there's really something that has to do with primes and so on and so forth. But starting from 7 runners, the things are not clear. Then another line of thought were like to prove weaker bounds. So we asked for this gap of loneliness of 1 over n plus 1, but you might say, okay, maybe I can guarantee less, but for any choice of velocities. And Wills himself already showed that by like a pigeonhole principle type argument, you can always guarantee that the runners are way 1 over 2n from the common starting point at some point in time. And then people started to try to improve this bound. And then over the years, some improvements were made, but you see there's like additive terms that show up here with a quadratic term in the denominator. And then Terry Tao also got interested in the problem, and he thought, well, I can do something more. And what he could do is like introduce this logarithmic factor over here, but nobody came above like this 1/2 times n here. So if you could manage to prove the gap of loneliness of 1/1.9 times n, this is really the breakthrough result on this conjecture. This is what Terry Tao tried, but also he couldn't do it. And then there's also the question of finite checking. And one important reduction is that it suffices to look at integer velocities only. So initially, nobody stopped you from choosing the VI to be real numbers, rational numbers, or any irrational numbers even, but it does suffice to look at integer velocities. So this was conjectured by Wills, or just stated, and it was proven like with an inductive approach, assuming the Lonely Runner Conjecture to be true in one less dimension by Bowman, Holzmann, and Kleitman, and then together with Romanos, we did it like independently of the dimension. Independently of induction, I wanted to say. And then another reduction is due to Tao, and he could show for the first time that it suffices to look at a finite set of velocities. So he could prove that if every velocity is upper bounded by this term n to the c times n squared, where c is some constant, then this is like containing the extremer cases. So if one velocity is too large, then the conjecture holds. So this kind of gives you a finite checking result. You have only finitely many cases to check, but from this bound you see that the finite really means still a lot of cases to check, and this is not applicable for the first open cases, so to say. So what I plan for the talk is the following. I do want to give a geometric interpretation of this Lonely Runner problem in terms of integer points in zonotopes. And then I want to, well, this interpretation somehow leads us to an algorithmic problem to compute the so-called covering radius of a zonotope. And I will explain what this is. And then putting these two things together, we want to solve like the first open case of a variant of this Lonely Runner conjecture, which we call the shifted Lonely Runner conjecture. And I also come to this, what this means. So let's try to interpret the problem in terms of certain polytopes, and these are zonotopes. So, but to prepare this, I want to introduce some notation, because I don't know where we are all together with in terms of well, notation. So let's fix some. So K in Rn will always be a compact and convex and full dimensional set for me, and in particular I mostly look at polytopes. And a polytope is just a convex hull of finitely many points, or the bounded intersection of finitely many half spaces. So that's these two ways I can write down a polytope. So for example, here I've got a 5-gon in the plane. And then I want to look at a certain time, I wanted to look at dilations of such polytopes. And for a given number r, I call r times k the r's dilate of k. So you can either shrink it or scale it up. And I can also translate k by a translation vector t, and then I talk about the translation of k. And then another thing is the standard integer lattice that will always also be important for us, because we will study then how dilates and translations of a certain polytope behave with respect to the integer points. So let's look at this geometric way of looking at the Lonely Runner problem, and we do an intermediate step, and this is via view obstructions. And to prepare this, I want to collect these velocities v1 to vn into an n-dimensional vector, which I call v, and this is usually called the velocity vector of the Lonely Runner instance, so to say. And I would also call them non-trivial because none of these entries is equal to 0. We'll see in a minute why this is important. And then I say a view in direction v is just the half, it's just a ray of the half line emanating from the origin in direction v. So it's all these non-negative multiples of the vector v. And then I look at the formulation of the Lonely Runner problem. This is like here the first line. So there is a time such that if I multiply any of these velocities by this timestamp, then I will get something that is away from any integer. And if I want to reformulate this, then I can first write this out. And this means that there's a time such that for every I, there is an integer, zi, such that this multiple tvi is fulfills these conditions. So it's like on the lower bound, it's 1 over n plus 1 away from zi, and on the upper bound, it's 1 over n plus 1 away from the integer zi plus 1. So you find these integers that somehow certify that you are away from the integers. And now, given this velocity vector and this view interpretation, you can write this down as follows. You look at this ray here, and then you intersect this way with an arrangement of cubes. And here's the cubes. So it's like Cartesian products of like these line segments, of these line segments. And then you arrange each of these cubes into a lattice-like fashion. And you translate each of these cubes by an integer vector. And here the picture maybe explains it better. You take one of these cubes. It's like a Cartesian product of these intervals of the same length. And then you put these cubes, I mean, they do not contain the origin here, so they start like the lower left corner is 1 over n plus 1 in each coordinate, and the upper right corner is n over n plus 1 in each coordinate. So you put these cubes inside each cell of the lattice, so to say. And you get this lattice type arrangement of cubes, and you get this view arrangement. And now you can reformulate this Lonely Runner condition as saying that this ray will intersect one of these cubes. This is like a geometric interpretation, and this is due to Cusick. And he said that, well, this is like the conjecture. Every non-trivial view in Rn is abstracted or will intersect one of those cubes if you make them to have edge length at least n minus 1 over n plus 1. So you're taking 1 over n plus 1 from the left away and 1 over n plus 1 from the right away. And that's why you get this number here. Okay. And here, non-trivial is crucial because if you have a 0 coordinate in the view direction, then you go parallel to a coordinate hyperplane or coordinate axis, and then you will not intersect any cube at all. So it's in this sense it's restricted, but this is I think a natural restriction. This formulation, okay? Okay, and now based on this view abstraction formulation, I will now introduce where zonotopes come in, and also say what a zonotope is in a second. So I look at this view direction again, view abstraction interpretation again, here on the left. And now the fact that the view in direction v is abstracted by any cube can also like be equivalently formulated by we take just one cube and well, here on the left hand side we took one cube and like look at all the translates of the cube by integer vectors, and we fix one of these rays. Or we can also say, well, we fix one cube in one cell and then look at all the integer translates of these rays. And this is like the right picture. So this is like the same question: does any of these integer translates of the ray in direction v intersect this cube that maybe sits here in the cell at the origin? So this is like equivalent. And now for geometric purposes, this is good because we now have only one geometric object or convex object to look at here. And now the thing is, we could project everything in the direction of V. We can project out V and then look at what this intersection actually means. And for this, I need some notation. L sub V will just be the linear space of dimension n-1 orthogonal to V. So this is like where we project everything onto. And then for this velocity vector, we get a lattice depending on V by projecting the integer lattice onto this linear subspace. And since V was chosen to be an integer vector, this will really be something discrete again. So you see an n-1 dimensional lattice here. So here it's a point where it's really important for us that we did this reduction to integer speeds or integer velocities of the runners beforehand. And now we haven't projected everything yet, but we need to project the cube as well. And if we do that, then we get another polytope, and the projection of a cube is what is usually called a Zonotope. And if you project an n-dimensional cube, then you get a Zonotope with n generators. So here I give you two interpretations of what a Zonotope is. So either in this way a linear projection of the cube, or what you then get is you can also think about the Zonotope as being the Minkowski sum of finitely many line segments. So you get these line segments in space. So 0 is like the origin, and Z1 will be some point in space. Then you get this line segment, and then you get some other line segments. You add them up point by point, and what you get is a convex polytope, and this is called the Zonotope. And here written down the precise points that are contained in this Zonotope. So what we now look at is the Zonotope that comes from projecting the cube orthogonally to V with respect to the projected lattice points. And if we do this, then what we get here, maybe I draw a line. What we get here is like the orthogonal hyperplane orthogonal to V. And then we project all these points here. So we get these lattice points here. And so we get an n-1 dimensional space sitting somehow skew inside R to the n. So what we want to do is to look at this more, a little bit more conveniently. So what we do is like to take a linear map and put all this into coordinate space. So we take a linear transformation that maps this n-1 dimensional space to Rn-1, and then the corresponding lattice to Zn-1. This is possible, and that then we get a more convenient picture. And then the Zonotope is mapped to some Zonotope in n-1 dimensional space with n generators. So you get one more generator than dimensions of the space. So you should think about the Zonotope as being basically a cube or a parallelepiped, like a linear image of the cube. And then you've got one more generator that you add to this parallelepiped. And of course, these generators, they will depend on the velocity vector that you start with. And now the reformulation that we wrote down together with Romanos is that if you have a velocity vector v, then the Lonely Runner conjecture holds if and only if this condition here holds. And what does it mean? You take the Zonotope ZV that I just introduced, and you scale it by this certain factor that appeared already in the view abstraction formulation, and then you look at a certain translate of the Zonotope. XV here is the center of the Zonotope, and then you get also a dilation factor here for this. Then the condition is that this is actually exactly the projected cube in direction v, if you write it down. And this should contain an integer point. This is like the condition of the Lonely Runner conjecture to hold for this specific velocity vector v. And so now we have a question on integer points in Zonotopes, and this is something closer, at least to where I come from. So we can do some geometry of numbers and geometric arguments on these kind of things. But before I get into this, I want to give you an example. So if you take the velocities 1, 2, and 3 for the runners, so we've got 3 runners on the track now, and so we have actually a projection of the lattice in R3 onto a 2-dimensional plane orthogonal to V. Then what we get is a Zonotope with 3 generators, and in the plane this is also called a hexagon, not just a symmetric hexagon, ZV. And this is now generated if you work it out by the vectors that correspond to the 3 columns of this 2x3 matrix here. And here's a drawing of the Zonotope that you get by projecting along 1, 2, 3. And if you look a little bit into what this is, then one point about Zonotopes is always that you can dissect this into parallelepipeds like this. And one point that I want to point out here for the Lonely Runner problem is if you look at the volumes, or here the area of this hexagon, then of course, as you get this dissected into parallelepipeds, the volumes of the parallelepipeds will add up to the total volume of the Zonotope. But the fact is that the parallelepipeds, they correspond in volume exactly to the velocities that you started from. So here this parallelepiped has area 1, this one here is area 2, and this one here is area 3. And this corresponds exactly to the velocities here, so that the total volume of the Zonotope is just the sum of the velocities that you started from. So that's a neat fact that you need for geometric considerations. So how to go on? So now we interpreted this Lonely Runner conjecture in terms of these integer points in Zonotopes. And now there's one thing about this formulation here that at least I find a bit unnatural, and this is like this translation here. So we have this Zonotope somewhere there, and this very certain translation needs to contain an integer point. That's the Lonely Runner condition, and this is a bit unnatural if you want to do geometry of numbers, and we want to get rid of this particular translation. And to explain this, I need the concept of covering radius. The covering radius, this is a parameter in the geometry of numbers that has a lot of applications within the theory, and is also a classical concept that was already studied way earlier than right in the first half of the 20th century already, I think. And well, one way to think about it is exactly as I just tried to suggest you. So the covering radius is the biggest number gamma, positive or non-negative number gamma, such that you dilate your given convex body K by gamma, and then this dilate can be translated such that this interior does not contain an integer point. So let's look at this a bit on an example. So if we have this green disk here, then its radius is quite small, so you can put this in some position such that it avoids any integer point. But you see it avoids them completely, so you might enlarge this a little bit and find a translate where this still fits inside the integer lattice. But if you and then you might get this gray disk. Then you get some integer points in the boundary, but none in the interior. But if you enlarge it further, then every translate of this red disk will contain an integer point in its interior. And this is not allowed here. So you need to stop growing up this green disk at this gray step, so to say. And the radius here, or the dilation factor, this will be called the covering radius of this disk. And why covering radius? Well, you can think about this number a bit differently by a covering property. And this is like the second interpretation that I want to present you. This number that I just introduced, it's the same as saying it's the smallest real number R. It is not negative, but such that every point can be covered by a lattice translate or an integer translate of this dilate r times k. It's the smallest real number r such that this arrangement of integer translates of rk, and so it covers the whole space Rn. In this way, it's a covering concept, and it's a covering radius because it's like the smallest radius of the bulk of the disk here in this example that will allow to cover the whole space. So in this example, you see, okay, there's gaps in between. You see this arrangement where we take the gray disk and look at all the integer translates, but there will be gaps. So we need to enlarge it to make it covering. And if you do it too large, then every point is somehow contained in some interior in the interior of some integer translate of the enlarged disks. So we don't need this large dilation maybe, but we can make it a bit smaller, and then we find its actual covering radius like this, and then we get some points that are only contained in the boundary of any translate, but not in the interior. And then this is like the extremal dilate that we can think of. And now with this property, I also maybe to give you a bit more examples on how this covering radius works. We have seen the cube already, the 0, 1 cube, and let me maybe try to draw the 0, 1 cube and show why its covering radius is equal to 1. Let's see, draw here. Where's my mouse? Oh, my tablet stopped. Here we are. So let's say here we've got this 0, 1 cube, the square. And if I now look at all the integer translates of the square, then you will quickly see they cover space already, right? So I mean, this is exactly like the unit cells of standard unit cells of the integer letters. They do cover, and also we have points here that are not contained in the interior of any translate. So this there's no change of dilation needed in order to get the covering radius. So we get really covering radius equal to. And if you look at another example, like the standard simplex, so let's say here's the origin now, and then we've got the first coordinate unit vector up to the last coordinate unit vector. And then we take this, the convex hull, then we get the standard simplex. And then you see, well, if you put this simplex in this dilation at every integer point, then you get some arrangement of these copies that does not cover the whole space. So you need to enlarge them, and you can think of this as enlarging until you find this vicinity of this point here. And in order to make this catch this points anything close to this upper right corner, you need to look at the dilation factor equal to the dimension n. And the last example is the unit ball that I want to show you, and this is one of these circles that I showed you earlier. I will not draw the circle because this will not be a circle afterwards, but here you can see that the covering radius will be root n over 2. Is the concept clear of covering radius? Okay, so what's now about the interpretation that I showed you earlier? So I said that I kind of want to get rid of this additional translation vector that sits inside here. So I just wrote down this interpretation by this integer points in this Zonotope again, and I want to get rid of this somehow. And this is now, thinking back of this concept of covering radius, this is now natural to say, okay, this is one particular translate of the Zonotope that contains an integer point. But if you want to get rid of these translates, then we might only look at what's the covering radius of this Zonotope. And this is what we call the shifted Lonely Runner conjecture. And this says that, okay, you take this velocity vector v, such that these points, again, the velocities are pairwise distinct, and then the covering radius of the corresponding Zonotope is upper bounded by this vector that appears here already, n-1 over n+1. So in other words, no matter where you translate n-1 over n+1 times this Zonotope in the plane in its space, it will always contain an integer point. Not only this particular translate, but every translate. And this is why we call this shifted, because you can shift it anywhere you want, and you will always see an integer point. So this really feels a lot stronger than the original Lonely Runner Conjecture. But actually, we do not know. We do not have a counterexample saying that this is really stronger. Everything we know about the Lonely Runner Conjecture being that is not a true statement. What I want to say is that we do not have an example where allowing for any translate requires a larger dilate. So this is what I want to say. And given these various interpretations that I showed you, what does this effect of allowing translates of the Zonotope mean? Well, in the runner setting, this means that these runners are now allowed to start at their own individual starting points, so to say. They do not need to start all at the same at the flag at the north, if you remember the picture, but they may start somewhere on the track. Everybody chooses before starting to run their own starting position, and then they run from there. If you're more inclined towards the view abstraction setting, then this means that the view does not need to emanate from the origin, but it can start anywhere in space, and then you look at this view in direction v from this point in space. And for the Zonotope, I said already that any translate is what we are looking now at. And well, this shifted Lonely Runner Conjecture, this is true for two runners, and there's a very clear geometric reason for this, because if you look at the Zonotope for two runners, then this is n-1 dimensional, so it's one-dimensional. So it's just a line segment. And I told you that the volume of this Lonely Runner Zonotope is given by the sum of the velocities. So if you have two velocities, integers, pairwise distinct and positive, then the sum of the two must be at least 3. So this means you've got a line segment of length at least 3. And if you want to cover the line by integer translates of a line segment, all you need to do that is a line segment of length 1. So you can scale down this Zonotope ZV by the factor of 1/3 and still guarantee a coverage. And this is exactly the bound that the shifted Lonely Runner Conjecture asks for. But the point is, for starting from 3 runners, the shifted version is open. So there's strong indication that it does not make any difference allowing shifts, but we absolutely do not know. Starting already from 3 runners, this is open. And what I want to do in the following is to look a little bit into how we approach this for 3 runners. And actually what we wanted to do is to check examples in the first place. And in order to check examples, we need to compute the covering radius as a parameter on these Zonotopes. And this is the algorithmic problem that I now want to talk about. And if I write it down concretely, then the algorithmic problem is the following. You are given now a rational polytope. I don't only want to give you a Zonotope, but just some polytope defined by rational data. So it's defined by this inequality system, and we know that we take an inequality system that we get a bounded set. And now, if you want to put this into a computer, then you need the rational data. So it's a rational polytope. Now, what we want to get is we want to devise an algorithm that computes, well, this number, covering radius of B. And people have looked into this already. And Kannan in the 90s, he realized that the Frobenius coin exchange problem, and we do have an expert in the room on this problem, Iskander, Kannan realized that the Frobenius coin exchange problem can be reformulated as, well, bounding the covering radius of a certain simplex. So kind of the easiest polytope that you can think of, but if you associate the data from the Frobenius problem to a simplex, then you get an instance that shows that the decision problem of bounding the covering radius is already NP hard, even for simplices, because this Frobenius coin exchange problem is one of the NP hard problems that is quite well known, I guess. Then even worse, if you look at parallelepipeds, then there was a work Fabi Femregiev, and they showed that approximating the covering radius of parallelepipeds, so linear images of the cube, is pi2 hard. So whatever pi2 is like, if you know a little bit about complexity theory, this is like on the second level of this polynomial time hierarchy. So pi2 hard problems are supposed to be strictly harder to solve than any NP complete or NP hard problem. So it's like one level harder than NP hard. So even for parallelepipeds. And so it is, I think, no surprise that the algorithm that does exist to compute the covering radius, and which is due to Kannan, has like a double exponentiation in the input in its time complexity bound. So Kannan proved that if you have a rational polytope P and its data is somehow bounded by this number delta, then you can compute the covering radius in this time here. D is the dimension of the polytope. M is the number of facets. It's like here, M is the number of rows in A, or M the number of defining inequalities, and then you get this log of the input size, and then you've got this double exponentiation here by the dimension. And so I told you we wanted to compute like for 3 runners concrete examples, and this algorithm doesn't work. So this is too complex, and also by nature it's not easy to implement. So we wanted to look at a simpler algorithm, and what we realized is that there's a geometric way to think about the covering radius that allows a neat algorithm to actually get this number. And this geometric idea is based on the concept of last covered points. And let me explain what this means. So down here I've got the formal definition, but I want to explain it on the figure. So on the left-hand side, I want to look at, in a minute, a covering of the plane by integer translates of a certain triangle, and on the right-hand side by integer translates of a square. So if I look at these translates dilated by its covering radius, then it looks like this. So everything is covered. But then there's these special points that are somehow caught last by this covering. And this is why we call them last covered points. So if you start out from something that does not cover, then you increase the dilation factor until it covers all space. The points that are caught last, this is like the last covered points intuitively. And this is the red marked points here in my figures. So for the triangle, you have like a discrete set of points, but here for the square, you have one-dimensional parts of the plane being responsible for this covering. So formally, P, a point, one of these red points is called last covered if this point P is not contained in the interior of any translate of the correctly dilated polytope P. And the thing is that knowing these last covered points means knowing the covering radius. So we need to identify these last covered points, and this is what we did in the main lemma, which I want to explain on this slide. So what we can do is we look at the rational polytope P. Now, for convenience, we do write the right-hand side equal to 1 just by, I mean, there's no reason to assume 1 here. We can just divide out by the non-zero right-hand sides. And now what we can do is we want to characterize these last covered points by somehow finite data. And this will then lead us to an algorithm. And the statement is that if you have such a polytope, then you do find facet normal vectors, so d plus one of them, where d is the dimension of the polytope. And then you also find d plus one integer points. And these data, they define you an inequality linear system, an equality system. Yeah? And the variables in this equality system, linear equations, this is d plus one variables. One variable is mu, and the other variables are hidden in this d-dimensional vector x here. Yeah, and the AI and the ZI, they are data that define this linear system. And the claim is that you always find this data such that this system has a unique solution. And in this solution, mu is exactly the covering radius of P, and P bar, which is like the solution corresponding to the variables X, is the last covered point. And geometrically, how you should think about this lemma is that you find finely independent facet normals of translates of your polytope, such that the corresponding facets of the translate, their intersection define this last covered point P bar. And these blue integer points, they correspond to the translates that you actually chose. And now, since this lattice Z to the D, this integer lattice is periodic, and P itself is a polytope, so it's bounded, you can restrict this choice of normal vectors and integer points to a finite list, and then turn this into an algorithm. This is like the idea behind this interpretation. And if you work this out, then you can bound the time complexities that this requires, and what you get is a time bound for computing a covering radius that looks like this. Now, compared to Kannan, we see that this only has one exponentiation of the input and not two. So this is, in this sense, better, but we cannot, for example, expect a polynomial time algorithm here, because I showed you that this problem is supposed to be very hard under the natural complexity assumptions in the complexity theory. But the advantage of this algorithm is that it is really quite simple and actually easy to implement on a computer. And we did so, and we do have code in Sage Math that is also available for the public and to look and make their own computations for covering radii of small dimensional polytopes. And so with this algorithm, we actually could do experiments. And as I said, we did not find any counterexample for the shifted lonely runner conjecture. And what we now wanted to do is to actually try to get a computer-aided proof maybe for 3 runners in the shifted setting. And this is like the last thing I want to talk about. We want to solve the shifted lonely runner conjecture for its first open case, and this is like the case of 3 runners. And here's the result. So we managed to do it. The shifted lonely runner conjecture holds true for 3 runners, and there's only one extremal scenario, and this is the Zonotope, the hexagon that I showed you, the one corresponding to the velocities 1, 2, and 3 of the runners. And the idea was that well, we now have access to methods from the geometry of numbers, because we do not have this particular and kind of special translate of the Zonotope, but we are looking more broadly on this covering radius concept. And this allows to make stronger reductions than the ones that Tau did for arbitrary dimension and in a non-shifted setting. But this is really restricted to the Zonotopes being hexagons in the plane and being allowed to be translated in wherever we want. And so our initial reduction was not so good. So we were left with like 90 examples to check, but we could check them with the computer, and then we were happy. But then we looked a bit more, and we found, okay, we could do a theoretical reduction that will leave us only with 4 cases left to check. So in the end, we don't need the computer really to prove this theorem that I wrote down here. We can compute the corresponding covering radii of these 4 hexagons also by hand and see that this works. But in the end, we also have this algorithm in order to check more closely about these examples. Yeah, so what's like the open questions that are left, for at least in my opinion. So I told you that in the plane we could improve Tao's bound on these hexagons really a lot, and helping us to make this reduction. So what about in general? Can we get a better finite checking result than in Tao's result? Saying that this bound here into the something quadratic in the dimension, this is really too bad for allowing computer approaches. So can we get a better bound? Another question that is not answered by what we did is, does this allowing the runners to start at their own individual starting points really make a difference in the conjecture or not? My conjecture is that it does not make a difference, but then again, I do not have an explanation why this should be true for starting with 4 runners or more. And also, I think it just may very well be the case that starting for 8 runners or some higher number of runners, the conjecture is plainly false. So people, I think, always try to think too positively sometimes about hard conjectures, and people should think about counterexamples there. I think this is also a line of thought that is worthwhile to go. And yeah, with these 3 open questions, I thank you for your attention, and I'm open for questions.
Thank you very much. So, are there any questions from the audience?
May I give it a go? Matthias, very nice talk first off, thank you. With this polyhedral approach, were you able to give any kind of theoretical bounds as well? I mean, using some bounds for like the covering radii for Zonotopes?
You mean like that?
Like weaker ones, obviously not tight ones, but I mean, do you get anything with that approach?
We do get anything, but we do not. This is. I don't know if I want to thank you for your question, but this is embarrassing. So what we cannot do on the geometric side is to reprove this this weaker bound 1/2n geometrically. Okay. Because these Zonotopes are somehow constrained. They are in a certain way special. So it is not like that they cover the whole class of Zonotopes, but they are like a certain structured subclass that is a bit harder to deal with.
Yeah, because I mean, I think there's like loads of results to Zonotopes, so I thought maybe there would be something that you could refurbish, but if you don't want me to ask this question, I mean, I haven't asked it.
Right entry, yeah. It's a natural way to think about that.
Did you play around with dimension 4, or is it just, does it explode already?
So the reduction to make this a finite checking result in dimension for 3 runners is really strongly tied to the Zonotopes being planar. So if we do this in dimension 3, then we could not finish the reduction, at least to make it a bound that is checkable.
Okay, I understand.
But there's open questions that come along this reduction approach that, for example, about the Zonotopes that you just asked. So there's things that we want to follow up in the future.
And negative velocities, would that change anything? Because I mean, like in this reduction in the very beginning that you showed, that where you essentially project things down by just looking at the differences. I mean, I assume
no, it doesn't change at all by the same argument you just said. So, yeah. You can just add or subtract the same amount.
Okay, true, yes.
Every velocity, and you get the same problem.
Are there any more questions? Okay, I don't see anyone about to ask questions, so let's thank the speaker again, and then I'll stop the recording. Thank you very much.
Thank you.